I thought we'd start off today with this opener. If x is any value, find the magnitude of the vector, cosine x comma sine x. So we know how to do magnitude already with a vector. And so now let's extend this idea a little bit to something that makes us feel a little more uncomfortable. Because when we see vectors, we usually think of with seeing numbers. For example, if I said if the opener was find the magnitude of this vector, that'd be easy. Answer is 5. So it'd be a good idea to probably hit pause and try and solve this, and then go ahead and see how we do this. All right, so here's how we're going to do this. Just like we would do any other magnitude of the vector. So the magnitude of this vector is going to equal the square root of the horizontal component, or the x component squared, plus the y component squared. And hopefully when you see that, some bells go off and you say, wait a minute, that's a Pythagorean identity. Cosine squared plus sine squared is 1. And the square root of 1 is 1. And so that's the magnitude of that vector. All right, today we're going to focus on an operation with vectors called the dot product. We know how to add or subtract vectors, and we know how to multiply a vector by a scalar. But we don't multiply vectors by each other. There's one operation called the dot product. So for example, if I have these two vectors u and v, I want to define this new operation called the dot product, and we use just a dot, kind of like we've used multiplication in the past, such that u dot v is equal to 14. So, and you'll notice in IB, in text, they don't use a dot for regular multiplication of numbers. I guess they don't want us to confuse it with the dot product of vectors. But the dot product is actually pretty easy to calculate. All you're going to do is multiply the x components, and then multiply the y components, and add those two results together. And so in this case, 4 times 5 is 20, negative 3 times 2 is negative 6, and 20 plus negative 6 is 14. Later on, we'll show you where this dot product calculation comes in handy. So in general, the dot product of two vectors is the sum of the product of the x components and the y components. So find s dot t, given that s is the vector negative 3i plus 4j, and t is the vector 7i minus j. Now notice, I'm giving these vectors s and t in a different form. I'm giving it in terms of the unit vectors I and j, as opposed to the last example where it was in component form. So don't let the different forms throw you when you're working through problems. So another way we could think of it is we could write our vectors this way. So in any case, we're going to multiply the x components. We're going to get negative 21. And then we're going to multiply the y components to get negative 4 and add those together and get negative 25. And so that's the dot product of those two vectors. Find the dot product of these two vectors. And once again, I keep saying this, but it's a good idea to hit pause and on some scratch paper, if you have next to you, work out problems before you listen to me go through the solutions. Being active in your learning will stay with you much longer than being passive and just watching it. All right, so the dot product is going to be negative 1 times 2 plus 4 times negative 7. So we get negative 30. What if we switch and we do the 2 negative 7 vector dot negative 4 1 vector? Well, we're still going to multiply the x components and multiply the y components and then add those together, and so we get the same answer. And so obviously the dot product is commutative because the operations involved are multiplication and addition, and those two operations are commutative over the set of real numbers. So dot product is commutative. What if we did the dot product of a vector with itself? Well, in this case, we're going to get -1 times -1 is +1, plus 4 times 4 is 16, and so we're going to get 17 for our dot product. Now that calculation should look familiar. It turns out, what if I asked you to find the magnitude of the vector -1, 4? You would do the square root of -1 squared, which is -1 times -1, plus 4 squared, which is the 4 times 4 that we just calculated, and so we'd get the square root of 17. So if we square the magnitude, that gives us the dot product of two vectors with themselves. Let's look at this example. Let's combine some operations here. If I have three vectors, a, b, and c, I want to find a dot b plus c, and then I want to find the sum of a dot b and a dot c. So let's start with the first one. We're going to do a, well actually let's just write the vectors out here. So vector a, and I'm going to write these vertically, so you're more familiar with it when you see that in your text, dot. And now I'm going to do b plus c. So that's going to give me a -2 plus 4 for the x and a 2 plus -1 for the y. So when I do b plus c, those are two vectors added together, which gives me another vector. And then I'm doing the dot product of two vectors. So that's all legal. So I'm going to have the vector 1, 3, dot product with the vector 2, 1. And so then I'm going to multiply 1 times 2 plus 3 times 1, and that's going to give me 5. All right, let's do the other calculation. So here I guess we need to consider order of operations. Now, obviously we couldn't do the addition first, because if I do the addition first, b plus a is going to give me a vector, and then if I go left to right, I'm doing vector a dot with the vector b plus a, so that's legal, but that's going to give me a number or a scalar, and then I can't do the dot product of a scalar with another vector. So you have to keep in mind as you're doing these operations, and I just lost my dots, when you're doing these operations, you have to keep in mind what objects you're using and dealing with, and what kind of an answer you're getting from it. So we're going to do the dot product of a and b. So I'm going to do 1, 3, dot with -2, 2. And then I'm going to do the dot product with a and c. So 1, 3, dot with 4, -1. And then I'll add those two answers. So for the first dot product, I'm going to get -2 plus 6. And that's a number. Plus, and then with the second dot product, I'm going to get 4 plus -3. So I'm going to get 4 plus 1, which is 5, which was the same answer I got with that other calculation. So that leads us to think that maybe, just maybe, a dot b plus c is going to be equal to a dot b plus a dot c. So it's almost like we can distribute with this dot product operation. Now, just because it worked for one example doesn't mean that it works for every example. So if we wanted to prove it, I guess we would have to generalize and do a setup this way. So I'm going to work through this very quickly. Not that I would probably ask you to prove something like this on a test, but I think it's important that you can get to that level of proof to generalize some of your ideas. So let's start with the left side. And let's see, I'll do that in blue maybe. So I want to do a dot b plus c. So, and I'm going to write these vertically. So I'm going to have a sub x, a sub y, dot. And then if I add b plus c, the x component will be b sub x plus c sub x. and then b sub y plus c sub y, and I'll do the dot product with those. And so for the dot product, I'm going to be multiplying I should probably make an arrow so you can see where I'm looking. I'm going to multiply the x component times that, and these are numbers, so I'm going to be able to use the distributive property there, and then I'm going to multiply a sub y times those. So I'm going to get a sub x times b sub x plus a sub x times c sub x, and then plus, now I'm going to go ahead and multiply the y components, so I'm going to get a sub y b sub y plus a sub y c sub y. And that's what I've got. Now I can rearrange these and maybe factor out some stuff, but essentially I'm going to leave that like where it's at now, and let's work the other side. Let's take a look at a dot b plus a dot c. I'll do that in a different color. So a dot b, let me write these next to each other. So a sub x, a sub y, dot b, b sub x, b sub y. And then I'm going to add to that a dot c, a sub x, a sub y, dot c sub x, c sub y. All right, so for the dot product of the first two vectors, that's going to give me a sub x times b sub x. And then I add to that, multiplying the y components, a sub y, b sub y. Plus, and then I'm going to do the dot product of vectors a and c, multiply the x components, a sub x, c sub x, and then add to that the product of the y components. And let's see where we're at. We've got a sub x, b sub x in both. We have an a sub x, c sub x, that's right over there. We have a sub y, b sub y, check, and a sub y, c sub y, check. So there we go. So now we have actually proven that those two expressions are equivalent. All right. Where can we use the dot product? Well, what if we let theta be the angle between two vectors? Then it turns out that the cosine of that angle is going to equal the expression u dot v divided by the magnitude of u times the magnitude of v. So it's easiest if we go ahead and apply this to a specific example. All right, so we've got two vectors, 4, 2, and 3, 5. By the way, let's just do a quick graph to get a visual for this. 1, 2, 3, 4, 5. All right, let's plot these two vectors. So 4, 2 is about here. There's 4, 2. And then 3, 5 would be there. And I'm looking for this angle theta in between there. So according to this, the cosine of theta should equal the dot product. Well, the dot product will be 4 times 3 is 12, plus 2 times 5 is 10. So I'm going to get 22. And in the denominator, the magnitude of the first vector will be the square root of 20, 4 squared plus 2 squared, and then multiplied by the magnitude of the second vector, which will be the square root of 34, 3 squared, 9, plus 5 squared, 25. So that's going to give me what the cosine of theta is. So to find theta, I'll do the inverse cosine of 22 divided by the square root of 20 times 34. Now I could simplify these, the radical, but there's no need to. This isn't going to be an angle that I recognize, so I'm going to have to use a calculator. So why waste time doing some simplification? I'm just going to punch it in like that. So I grab my calculator, And let's make sure we're in degree mode. Check. So I'm going to press second cosine, 22 divided by, and it's just easier to have it all inside one square root. That's why I wrote it that way. 20 times 34. Close out the square root, close out the inverse cosine. Double check everything looks good. 32.47 degrees. So I'll round it, I'll say 32.5 degrees. So theta is approximately 32.5 degrees. And looking at the picture, and my picture isn't perfect, but it's close enough that seems to make sense. So that looks pretty good. All right, so that's how we can use our dot product to help us figure out the angle between them. Now, what if the dot product wound up being 0? Well, if the dot product is 0, I'm going to have cosine of theta equals 0 over the square root of something, which is going to be 0. And when does the cosine equal 0? Cosine equals 0 at 90 degrees, or 270 degrees. So what does that mean about my two vectors? That must mean that they're perpendicular to each other. So if the dot product of two vectors is 0, then the vectors are orthogonal. So orthogonal, perpendicular, or normal. All three of those terms mean the same thing. Orthogonal, perpendicular, or normal. All right, so that's an easy way to figure out if two vectors are perpendicular. Just check their dot product. All right, how about finding the angle between these two vectors? Well, right away when you do the dot product, I'm going to do 2 times 6 is 12. Negative 3 times 4 is negative 12. I get 0. I don't need to fill out the rest of that formula. I don't need to do all that, because I'm going to get 0 over whatever. The magnitudes aren't important. That's going to give me 0, which is going to imply that theta is equal to 90 degrees. So the angle between the vectors is 90 degrees. So it turns out two vectors u and v are orthogonal, or perpendicular, or normal, if and only if the dot product is 0. So that takes it a step further. So we're not just saying, hey, if the dot product is 0, they're perpendicular. This is saying if they're perpendicular, it's guaranteed that the dot product is 0. And the vector 0, 0, sometimes people don't think that that's actually a vector, but the vector 0, 0 is orthogonal to every vector. And if you think about that for a minute and say, well, what would you get if you did the dot product of the 0, 0 vector with any other vector? Obviously, you're going to get 0. So that makes sense. All right, so going back to worksheet 1.2, you should be able to do now numbers 5, 10, 11, and 16. And then in the book, in the text, in the review section 12A, which starts on page 318, I'd like you to do those problems.